Because last year we covered
Discontinuities are at -2.
Oh, so
And where is it?
Okay, let's talk about this. What discontinuities do we have, and where are they? What's one? Caleb, what do you got?
There's a jump at x equals -2.
Jump at x equals -2. Yep. Nice. What else? Henry. Yes. What's the other name for a hole? Anyone remember? Starts with an R. It's also called a removable discontinuity. I'll usually use the word hole, but if you see that, that's what it means. And we have one more. Jonathan. Yes. And anyone remember the other name? Yes. So infinite discontinuity, removable discontinuity, or jump discontinuity. Or you can call them a vertical asymptote and a hole. Nice. Okay. So we're going to talk about these different types of discontinuities in terms of limits. Because you guys were just doing the Desmos activity, which was reviewing limits. Remember, a limit is basically the y value that a graph approaches as the x coordinate approaches a given value. So that's an informal definition. And let me just underline approaches here, because remember, it's not necessarily the actual y value at that point. It's the y value that we're going to. It's what's like our ending point, what we're going towards. It's maybe another way to say that. Okay, so we're going to talk about, we're going to do limit notation for this removable discontinuity. And so remember, with limits, we have a left-hand limit and a right-hand limit. And then we can also talk about the limit from both sides. So as we're looking at this graph here, as we're approaching, the hole's at x equals 2. So as we approach x equals 2 from the left, what does the limit appear to be? What's the y coordinate that we're approaching? 1. As we approach from the right, what is the limit? 1. And so that means, since the left and right sides are equal, we would say the limit of this function as x approaches 2 from both sides is also 1. And the limit does exist, even though the function's not continuous there. So let's write that down. Let's call this, I'm going to label this graph f of x, just so that we can talk about it. And so here's something that's good to remember. The limit always exists at a hole in a graph. But the function is not continuous, of course, because it's a type of discontinuity. In this case, if we look up at this graph, we would say that f of 2 is undefined. There's no y-coordinate for x equals 2, so it's undefined. There could be a world where the y value is somewhere else, and then we would say, oh, f of 2 is 5. But in this case, since there is no y value, we would say f of 2 is undefined. Okay, so next we're going to talk about that jump discontinuity. Turn to your neighbor. How would you talk about limits with this jump discontinuity? What's the limit from the left, from the right? What's the y-coordinate?
Notes are so much better than mine.
You guys are good handwriting. Okay, let's look at the picture. So as we approach -2 from the left, what's the limit? 1. As we approach from the right, what's the limit? -1. So we would say the limit of f of x as x approaches -2 does not exist because they don't match. What is f of -2? 1. It's where the closed circle is. So there is a y-coordinate there. So 1, -1. So we're going to say dne. Technically, it's not equals dne. We just say the limit does not exist. If you put an equal sign, it's fine, but technically there shouldn't be one. So in addition to the other stuff we said about the jump discontinuity, a limit never exists at a jump discontinuity. Okay, go through that same process with the infinite discontinuity. Talk about the limit from the left and right-hand side. with your neighbor. Ready, set, go.
Sorry, I'm saying this isn't my handout, so I'm just as it approaches it's a positive infinity. So the limit does not exist. I'm pretty sure, right? Yeah. And then, but it's and the F3 does not exist.
That makes sense.
Also, on this one, there is a limit, so it's
Okay. So the limit here as we approach 3 from the left, right, and from both sides, what could we say? What could we say for all 3 of those? What would you guys say as it approaches from the left side? Negative infinity. Okay. What would you say from the right side? Infinity. From both sides? Does not exist. Okay. So this might be a little bit different. It sounds like it's a little bit different from last year in pre-calculus. What we want to say for all 3 of these is does not exist. We do not need to specify which infinity it approaches. Oops. Because if you think about it, if I can do something forever, is there a limit to how long I can do that thing for? No. If I can go forever in a certain direction, is there a limit to how far I can go? No. So last year in pre-calculus, your teacher probably emphasized which infinity it went to just so that you would know the behavior of the graph. In calculus, when we're just talking about limits, just go ahead and say the limit does not exist, which is nice. We would not say f of 3 does not exist. We would say f of 3 is undefined. F of 3 is undefined. So DNE is only for limits. And so similarly, a limit never exists at an infinite discontinuity. We are always approaching infinity, so the limit will never exist. Answer this question with your neighbor. On what intervals is f of x continuous? Write that in interval notation.
That would just be like, let's say the this is infinity,
All right, did you guys get this? 4 intervals where f of x is continuous. So it's basically every point from negative infinity to infinity except wherever we have a discontinuity.
Why wouldn't you do like color brackets?
Because at -2 is where we have a discontinuity, so we don't want to include -2. So it's not domain. Domain would be different. Domain would skip this -2 part because that's included in the domain. But yeah, intervals where it's continuous. Yeah, good question. Okay, I want you guys to do the limit notation for, let's say, x equals -3. So that's one of these intervals here. What is the limit? Yes, as x approaches -3 from the left and from the right and from both sides. Okay. What is the limit for the left and the right side? 2. Yes. So it's 2 for left, right, and that means it's 2 for both sides. And what is f of -3? What's the y-coordinate? 2. Okay. This is basically showing the definition of continuity. So that So we are going to write down the definition of continuity here. Okay, so we have this 3-part definition of continuity. The definition says, first of all, we have to have a limit. The limit must exist at that point, which means the left and right hand limits are the same. We have to have a y-coordinate at that point. It must be defined. And then lastly, the 2 parts have to equal each other. So often we will use this definition to prove that functions are continuous. And you'll see some questions on the delta math that have you do that. I would say that number 3 is kind of the main one. That kind of sums it all up, but of course the other 2 parts have to be true for that to work. So this is technically section 1.2. It's not super different, but. So what we're talking about is finding limits from equations. So not from graphs, but from like given a function, what's the limit as x approaches, whatever. So when you're given a function, let's just say, let me just put it down here. So I'm going to write something above that. But let's say we're trying to find this limit. The first thing that we should always try is substitution. We should just take 2 and plug it in and see if we get an answer. If we do get an answer, then that means the function is continuous, and that means the limit exists, and the limit is just whatever number we get. Things get tricky when instead of getting a number, we get something like 0 over 0. If that happens, then we need to use some other method, which might include factoring, multiplying by the conjugate, finding a common denominator, some things that you guys did last year. So that's when we need to use our other techniques. So let me write that down. So what that could look like here. So one thing I noted here is you don't want to say equals 0 over 0. That is not a real thing. So never write that. It just means you need to manipulate whatever you're working with here. So notice if I plug in -2 to this expression, I will get 4 plus 4 minus 8, which is 0, over 0. So I don't want to write equals 0 over 0. Instead, I want to factor this expression here. Notice my notation here. When I factor this expression, I'm going to keep the limit part of it right there. I'm going to factor this here into x minus 4, x plus 2 over x plus 2. So that's going to stay there. The x plus 2's will cancel out. And now I can substitute in -2 to whatever's left over. What am I going to get once I substitute in -2 to x minus 4? -6. Once we get our final answer here, now there's no more limit notation. So again, you'll see some examples on Delta Math where you have to do like conjugate or greatest or common denominator, things like that. But this is some stuff he did at the end of the year at pre-calc. We'll open with some examples of that next class. One thing I want to note here is when you're doing limits from piecewise functions, actually, let me do another one here. So with piecewise functions, what we need to notice is where the function is changing. So it's -x squared to the right of 1, and it's 2x minus 3 to the left of 1. So if I'm being asked to find the limit of f of x at 1, I'm going to need to look at the left and right hand side of this because 1 is where the function changes. I'm going to need to do the limit of f of x as we approach 1 from the left side, which would be using the 2x minus 3 part. That's from the left side. So it'd be 2 times 1 minus 3 equals -1. I'm going to need a little more space here, I can tell. Whoa. And then I need to do the limit from the right side, which would be using the -x squared part. So this would be -1 squared, which also equals -1. So I need to check both. That equals -1. If I'm just doing a part that's not part of that with the -3, I just need to plug it into the relevant part. So this would just be -3 squared, which would be -9. Okay.